Hi, this is Mr. Ferguson.
And Mr. Hunter.
So, lesson 2.2, we are going to take a look at some fundamental laws of physical science and physics and chemistry, fundamental laws of everything, really.
And our objectives are to state and explain the law of conservation of mass, the law of constant composition, and the law of conservation of energy.
All right. Let's get to it.
So the law of conservation of mass is the total mass is conserved in all physical and chemical changes.
So the word conserved, when you see that in the scientific law, it means something is unchanging. It doesn't go up, it doesn't go down, it stays exactly the same.
So for example, if we melt 10 grams of ice, we will yield 10 grams of water.
So the amount of mass you had before the change is exactly equal to the amount of mass after the change.
All right, the second one now is a little more tricky because it's not just a physical change. We're now dealing with a chemical change. We're dealing with zinc reacting with hydrochloric acid.
So let's say we have our system set up like this. How about I put it where we can draw? So we're going to take a glass container. We're going to put some acid in there, HCl. And then we're going to put a balloon over the top of the container into which we put a nugget of zinc metal. Now let's say we mass this whole system before we start, and it weighs, mass is 25.0 grams.
Okay.
All right, now
we then put the zinc down into the acid, and you notice a reaction starts to occur. It starts to fizz and bubble and sputter and get hot.
And the balloon's going to expand because gas is being given off by the reaction. Go ahead.
And based on what we've talked about with the law of conservation of mass, the amount of volume may change, but the actual mass of the system remains unchanged. And this is only the case because we have a balloon on top. Now, if we were to take the balloon off and weigh it, you would find that mass has quote-unquote disappeared, which is impossible. So gases do have mass. You do have to trap them in these types of things. So what's the implication?
It means that basically you can't get rid of matter. You can't make it. You cannot create or destroy matter. You can rearrange the particles in the matter. You can make new things. You can destroy existing particles, but the total amount of matter is a constant for a given starting amount.
So, looking at this, all right, here's another reaction.
So we take a chunk of wood, and if you burn it, it turns into three products. We have ashes, carbon dioxide, and water vapor given off, and these two, of course, escape as what we would call smoke off of the fire. The ashes are left behind. Now, if you only looked at the ashes, you're going to have less mass in ashes than you had of wood to start with, because the ash, some of the matter that was in the wood has now escaped. But if you keep track of all that, if you combust it, burn it, and you keep track of the ashes, and you keep track of these two gaseous products that are given off, you're going to find that the mass of wood and oxygen that you had going into the reaction is exactly equal to the mass of the products after the reaction. Again, mass is conserved.
So the next law is the law of conservation of energy. It states the total energy in an isolated system is conserved. Energy changes forms, but the total amount stays the same. It cannot be created or destroyed. That's the first law of thermodynamics.
So looking at the graphic we have here, and this is kind of a review, I think, of some concepts you already covered in physics, but if you fired a cannon, there's some chemical potential energy released when that gunpowder or whatever the explosive is goes off. And some of that is converted to kinetic energy. That's the movement of the projectile. And as the projectile goes through its trajectory here, it gains height and loses speed right up till its apogee here. So it's going to be going slower here than it was here, but it's higher up off the ground, so we say it's gained some potential energy. And then that reverses on the way down. It actually gains speed, loses potential energy, And then there's an impact.
Yep, which releases energy in the form of heat and light and, well, just sheer momentum transfer into the ground.
So if you keep track of the total, it's like, imagine energy as these little indestructible units. The units can move other places. They can be turned into other forms of energy, light, heat, sound, momentum change. But the total number of units that were here in the chemical energy at the beginning are all still there. They're just not in the chemical energy form anymore.
All right, let's look at the last law then. So the last law is the law of constant composition, aka the law of definite proportions. It's a chemical compound always contains exactly the same proportion of elements by mass.
And this is a fundamental concept in chemistry, and it actually was one of the key things that led some of the early chemists to come up with the atomic theory as a way of explaining all of this. And so let's look at the graphic that we've given you here, and I would definitely recommend copying this graphic in because I think it gives a good example.
It's telling us we're starting with hydrogen and oxygen every single time, and we're always going to be making water with some leftover products or leftover unused chemicals. So in the first case, it says 8 grams of oxygen reacting with 1 gram of hydrogen will form 9 grams of water. Well,
And no leftovers here.
And that's saying that, well, this is also the law of conservation of mass, because 8 plus 1 is 9, so it states that one as well.
Yeah, that law is embedded in there as well.
Yep.
So if you add 10 grams of oxygen to 1 gram of hydrogen, you think, well, why don't you get 11 grams of water?
Yep.
You don't.
Because they have to combine in the same way every time. So again, they can only make 9 grams of water, and you'll have 2 grams of oxygen left over. Because it's saying you need 8 grams and 1 gram to make 9. Well, we only have 10 and 1, so the best we can do is 9 grams with 2 grams of oxygen left over, because the water is always the same combination.
Okay, and again, if we have increased the amount of hydrogen, it doesn't matter. You're still only going to max out at 9 grams of water.
And you have
so
one.
And a gram of leftover hydrogen, it doesn't have anything to react with. So as long as you're dealing with water, we have a constant ratio. It's always 8 units of mass of oxygen to every 1 unit of mass of hydrogen. And that's the only way you can make water from those two elements. It has that constant composition in its proportion by mass.
All right. So here are your post-video questions for Unit 2.2. Go ahead and read those and do your best in answering these. I don't think we have any hints for them this time.
No, other than, you're going to have to look through those 3 laws. Obviously, the answer is found in those 3 laws that we covered, and try to see if you can explain it, which law applies to this here, and explain what the question's asking you to in terms of the 3 laws we just saw.
All right, we'll talk about these tomorrow. Have a good night.